everyone, welcome back to our system design playlist. Today we are going to explore one of the most critical components of modern distributed system, that is load balancing. In this video we are going to see exactly how Netflix uses load balancing to serve over 230 million subscribers worldwide without going down. So grab your coffee and hit that subscribe button and let's dive into this. So let's start from the basic of what exactly is load balancing. So load balancing is essentially the distribution of incoming network requests across multiple servers. You can think of it like a traffic controller at a busy intersection. Instead of letting all the cars go on one road and create a massive traffic jam, the controller directs the traffic to different routes to keep the things flowing smoothly. The key goal here is to prevent a single server from being overwhelmed. I'm sure you all have viewed Stranger Things on Netflix. Now imagine if Netflix has just one server handling all the requests, and the moment the season 5 or season 4 of Stranger Things drop, the server would crash faster than you can even say Demogorgon. Now let's see what is the impact if we don't use load balancing. So let's understand this with the animations that I've actually made for you to give you a clear understanding of how load balancing actually works and what would be the impact. Now as you can see, all the requests are initially coming to S1 server and it gets overwhelmed because the server goes down and cannot handle such a multiple number of requests. But with the help of load balancing, our request would actually be diverted through all the servers equally, so that one of the server does not get that particular amount of load that it could go down. So this is the impact of load that load balancer actually brings into our system. Now not all load balancing is created equal. There are two main types that you need to understand. One is the layer 4, that is called the L4, and one is called the layer 7, that is the L7 load balancing. And choosing the right one can actually makes a huge difference in your system's performance. Now let's see what actually is a layer 4 or L4 load balancing. It actually L4 load balancing is applied on the TCP or the UDP layer, and it actually and it makes a routing decision based on the IP and the port. You can think of it L4 load balancing as to be like an envelope which is being decided where to send without actually opening the letter and see what the content is inside it on the basis of the headers or the port or the IP that where this content needs to be sent. We use the L4 load balancing when we need to process the request faster, and it's also protocol agnostic. Protocol agnostic means that it works with any kind of traffic and also has lower latency. Now let's come to L7 load balancing. L7 load balancing actually applies on application layer. This is where HTTP and HTTPS comes into picture, and it actually looks inside the actual contents of the request. What is the HTTP header, URL, cookies, and even the request body as well. So this actually tells us that L7 is actually intelligent routing, because it actually requests the call on the basis of what kind of request and what kind of server should handle that. So you can send images request, like if it's an image request, you can send it to an image server, and if it's an API call, you can send it to an API handling server, or if it's an authentication request, authentication server would be handling. And you can also do SSL termination, and which means that load balancer would handle the encryption and decryption work as well. So this is a huge difference between L4 and L7 load balancing. And Netflix actually used both on the basis of the usage or the task actually performing to ensure that the things actually work smoothly. Alright, now we have discussed what load balancing is and what are different types of load balancers. Now let's understand the different algorithms that are involved in load balancing. And they plays actually a very crucial role in deciding which algorithm needs to be picked on the basis of what kind of system we are using. Now I have actually made the presentations, like small animations for each of this algorithm to give you a very good understanding, like a visual understanding of what these algorithms are, how these algorithms are actually working. So this is the round robin algorithm. So let's start with the animation first. So as you can see from the animation, round robin is actually a simple approach. It's like, imagine we have like three servers, S1, S2 and S3, where all the servers have similar capacity and all the requests are actually being, so the requests that are coming to the load balancer, they would be passed through S1, S2 and S3 in a order. Like first request would go to S1, second would go to S2 and third would go to S3. So this is how a round robin actually works. Now this actually works only when all the servers have similar capacity and all the requests are having all the servers are having the similar processing power. But what if one server is capable of handling more requests, like more powerful and would have more CPU, like more CPU intensive? In that case, using round robin is not a good approach, because you are giving lesser load to a server which can handle more, and giving more load to a server which will actually lead to like the dropping of that server, like, or the termination of that server. So now we would be discussing the least connection algorithm. So least connection algorithm like does not actually blindly send the request to the round robin algorithm. This algorithm sends new requests to the servers that currently have fewer active connection. Notice that initially the requests go to S1, which has currently made one connection with each, and after processing, let's say S1 is more powerful, so it would be actually processing the request more faster than S2. So then next request would go to S1 because its connection would be 0, and for S2 it would be still processing a connection. So the next request would go to S1, and after, like, let's suppose S1 is currently holding 2 requests, so it's processing that, and then S2 is empty at that time, like S2 is not looking into any request or connection, then the next incoming request would go to S2. So this is a more intelligent way of handling the request, rather than just overwhelming the system one by one in the round robin form. Now next we have a weighted load balancing algorithm. So like the weighted algorithm is just simple, like we give a different capabilities to different servers, and if one server is like X times faster than a particular server or X time more powerful, then it would be handling X times more number of requests than a server with less power. So now initially we can see that S1 is holding W3, that is 3x powerful than S2. So in that case, S1 would be handling 3 times more requests than S2. So this is a simple weight by weight kind of a algorithm. Now let's move to sticky session. So sticky session is also called session affinity. This ensures that the requests from same user always go to same server, and this is a crucial part of the application. This is used when actually we are storing the users data locally on the server. User sessions, like we usually store the user sessions on the data on the local server. So in that case, a sticky session is actually used to make a persistent session. Now let's understand how Netflix actually uses all of these. So Netflix uses the combination of all of these algorithms depending upon the service they are using. Let's suppose for video streaming, they might be using a weighted algorithm based on the server capacity, like which server can handle like more weight. So a video streaming would be like a higher video, or a more intensive video would be played on a higher server, rather than a smaller video would be played on a lower server. And for user authentication, we would be actually storing the local session in our local servers. So in that case, a sticky session actually comes into picture. So this is how the choice of the algorithm on the load balancing helps us to understand which kind of load balancer would help us in picking up the helping us to reduce the load. Now we have understood the load balancing algorithm. Let's move to something very more interesting. Health checks and failure recovery. Here's something critical that many people overlook and when learning about load balancing. Now I ask you a simple question. What happens when a server fails? How would that case would be handled if a server gets failed? Because in production many a time server failed due to any kind of a reason, like wrong code is being deployed or some request that came which taking a lot of time to be processed. In that case the server is become non-responsive. So how in that case would the incoming request would be diverted to multiple servers rather than a server which is in a failed state? Now this is where the health checks become absolutely critical. Load balancer actually monitors the health of the server in a constant manner, like like a pooling connection between all the servers. It sends a request to a server like, hey, are you still active or available for handling the request? And a acknowledgement is being sent from the server that yes or no. So only a yes acknowledgement would receive if a server is available, and if a acknowledgement is not received from a server, the load balancer assumes that the server is not available and it removes that particular server from the connection pool. So in that way the server would not be responsive to handle the request further. So now initially we have three servers. Let's understand this. So initially we have three servers, S1, S2 and S3, and this is our ELB load balancer. So initially all of these are working. So incoming request would go to S1, S2 and S3 depending upon which server has more capacity and all, as we have discussed in algorithms. Now due to some reason S2 got failed. Now we have read that it makes a constant polling connection with all of these servers. So ILB send a request to S1, like a message to S1, hey, are you available? And S1 sends with an acknowledgement is acknowledgement. So if if this is the connection pool, so ILB says that S1 is available, it sends to S2, but S2 is currently unavailable, so that acknowledgement would not be received. So an acknowledgement is not received, it would remove S2 from this pool, and similar for S3 is available, so S1 and S3 now are available. So now ILB, when a new request would come, it would only be given to S1 or S3. So this is how the health checks and failure recovery comes into picture, and this actually helps us in gracefully traffic rerouting, and also helps in zero downtime deployment. Yeah. Now let's come to a very interesting stuff, I would say, discussing the Netflix load balancing architecture. So Netflix actually heavily relies on AWS Elastic Load Balancer, that is AWS ELB. But here's the thing, they just don't depend upon a single load balancer. They have load balancer at multiple levels which can handle millions of requests per second. They use Netflix actually has their own load balancer, that is Zuul Gateway. So Zuul Gateway acts like a front door to Netflix backend services. It handles dynamic routing, monitors resiliency and security. Think of it like a super intelligent load balancer that knows not just to route the request, but how to route them based on the complex business logic. It not only just from the statement we can see, it's not only just routes the traffic. If it's an API request, I would be sending it to a backend service. If it's an authentication request, I would sending it to a authentication server kind of thing. So it not only just reroute the request, but also see if it's a complex request, I would be sending it to a more higher kind of a load balancer, a higher server, and if it's a small request, it would be sent to a lower server, and everything finally routes down to microservices. Netflix currently has a more than, I would say, thousands or hundreds of microservices, one for authentication, one another for recommendation, one for video streaming, and so on and so on. And here's where the global traffic distribution across AWS regions actually comes into picture. Now let's see, let's understand this with the example. Let's suppose we are like I'm sitting in India and I'm hitting the Netflix icon and actually going to stream a movie. Let's suppose Stranger Things only. So I don't know where would my request would go. Initially, let's suppose the request would go to a load balancer that is sitting on Singapore, because we have 190 countries and load balancer could be anywhere. So let's suppose we hit a request and it would go to a load balancer in Singapore. Then that load balancer, like the Zuul Gateway, actually decides that where this request would actually route to. So if it's an India request, and it would be then routing it to the nearest server to me, like to my region, and this is how the global traffic distribution actually works. Now let's see how the auto scaling is, what is auto scaling and how it is used. So auto scaling is like, let's suppose in Netflix currently, let's understand this in an example. Yeah, so let's suppose Netflix currently has 3 servers, S1, S2 and S3, just for an example, and this is a load balancer, and they are currently handled 100 requests per second. Now what if I say, like, due to some kind of a new season that is came, let's suppose a season for Stranger Things or Breaking Bad came, and now the request actually reached to thousands requests per second. Now this is actually a huge number of requests, which has increased like 10 times. The request has increased 10 times. Now to handle this with only 3 servers would get actually a bit hectic for the load balancer, because now each server would be handling 10 times more requests than they were actually handling before. So in that case, load balancer actually spins more nodes for these particular servers, and would then like the traffic would be routed accordingly to that particular nodes. Like nodes, as you can say, like additional servers as well, or like server, or like the internal server has actually more nodes also. So you can say like the more, like it would then spin up more servers like S4, S5, or like even if S6 is also needed, so it would spin this server for temporary purpose, and once the load reduces, then this servers would be shut down, like would be shut back down to normal, like drop down, like scale down, I would say. Like a better term would be using the scale down. They would be scaled down. Then we have circuit breakers, actually to prevent cascade failures. So what exactly is circuit breakers? So let's understand this. Now what if the recommendations service start failing? Then the load balancer actually detects that a particular service is failing. In that case, the load balancer would gracefully drops down, or like I would say brings down that particular server down, and for timing you wouldn't be getting a personalized recommendation, but that does not mean that the complete Netflix server would go down into that. So this is how the circuit breaker actually comes into picture, and Netflix actually uses the real-time monitoring and alerting as well to continuously monitor what the issues they are facing in the real time. Now here comes the, I would say, a very new concept, or a very new thing that only Netflix actually use, that is chaos engineering in load balancer. You can understand chaos engineering has to be a intentionally introducing failures to test the system. So Netflix is very smart. So let's understand this. So Netflix actually use chaos, which is intentional introduction of failure. So this actually means that Netflix in production environment, or like they intentionally stop some of the servers to test their load balancer. In short, I would say, let's suppose currently S1 S2, but in a graceful manner, I would say, graceful manner, or in some sense that users are not impacted, but to just train their load balancer, that if any kind of such situation came in, that load balancer should able to handle that. So this is the like I would say a best practice to test the system. So they run a chaos monkey, or kind of a chaos monkey at any point of time, and the chaos monkey actually brings down some of the microservices or some of the servers uh, to gracefully bring them down. At this point, the load balancer would actually perform the health checks on the servers, and see if that server is down, up, or running, or healthy or not, and remove that from the connection pool, as we have discussed, and would be forwarding the request to S1 and S3. And soon as the server comes up, the request would then start coming up to S2 as well. So this is the best validation I would see from the load balancer perspective that Netflix brings into with the help of chaos engineering. And this actually builds the confidence in systems reliability. Like if any kind of this systems comes into in the real scenario, then they are good to handle that. And that's a wrap up on a deep dive into load balancing. I hope this video gives you a solid understanding of not just what load balancing is, but how it's implemented in the real world. If this video has helped you understand the load balancing better, please give it a thumbs up, and it really helps me to know that the content finds you valuable, and it helps the YouTube show that to other developers who might benefit from it. And if you haven't subscribed it, hit that subscribe button and ring the bell for notification. I am constantly creating new content on system design, distributed system, and real world architecture examples for companies like Netflix, Google, and Amazon. And I absolutely love hearing from you in the comment section. Speaking of which, what should we cover next? And I'm thinking about actually deep diving into database sharding and replication. Thank you everyone, and see you in the next video. Thank you.